Okay. Bismillah ar-Rahman ar-Rahim. Salatu wassalam ala ashrafil mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Welcome everyone. How's it going? Alhamdulillah. Good. Any problems with the last lecture? Was easy, right? Okay. Only that. Okay, good. So that's the best news I heard. So you need an assignment. That's very good news. Okay. So careful what you wish for. You're gonna get it, inshallah. Yeah. So first, let's start with a recap and then discuss the assignment later. So the recap of last time, first, we're done with topic 1 and topic 2. So this is the second lecture of topic number 3. We discussed that we are now modeling joints because when we have these joints, we're going to be connecting rigid bodies together and making serial linkages or open chain manipulators. We said that an ideal joint, or another name for it, is a kinematic pair, so that it emphasizes the fact that it only kinematically restricts the motion of two rigid bodies with respect to each other. If we have no joints, then we just have a free motion, then we'd have 6 degrees of freedom. So the relative twist between any two bodies, 1 and 2, 2 and 1, doesn't matter, expressed in any frame, would have 6 degrees of freedom. We have 6 independent numbers we can choose from this relative twist. If we have a revolute joint, then we have only 1 degree of freedom in these 6 numbers. If we have a prismatic joint, we also have 1 degree of freedom. If we have a ball joint or a spherical joint, we have 3 degrees of freedom, and so on. Just a point on the on software implementations. Usually, software implementations allow you to connect rigid bodies through joints. So in the same language we're using. But when you want to allow, for example, free motion, which is if you have a floating base, for example, then they would call it a floating joint or like a free joint. Okay, so you would also connect two rigid bodies and allow them to move completely free with respect to each other by adding in between them a free joint or a floating joint. Okay, so this, for example, what the MATLAB robotics toolbox uses. Okay, we'll be dealing with that later, inshallah. We discussed the forward kinematics, which is the map that goes from the individual joints of our manipulator to the pose of the end effector with respect to the spatial frame. So the spatial frame or the inertial frame is frame number 0, and the end effector is frame number n. We can have here, for example, this is a 3-link manipulator, but we have 2 joints on the 2 frames on the last link, because we're interested in having, for example, this is at the 3rd joint. So this is the first joint, this is the second joint, this is the 3rd joint. While here we don't have any joints, and we just have a constant matrix transformation or homogeneous transformation between frame 3 and frame 4. In general, we would have 1 joint connecting each of these 2 frames. So this is the general formula. The way we derived or the way we expressed this forward kinematics map is by using what we call the screw representation or the screw interpretation of twists. And as a preliminary for that, we discussed the axis angle representation of angular velocities. This makes sense. So angular velocities as 3 numbers, we can represent them as some angular speed around some axis. And then we have that the rotation matrix is given by the matrix exponential of this expression. We derived it last time. And this matrix exponential is in general an exponential map that goes from the Lie algebra to the Lie group. And we said that it has a closed form solution, and this closed form solution is known as Rodriguez formula. And this is something very easy to program. So it's like 1 line in Python. It's very easy. By analogy from SO3 to SE3, we would simply have exactly the same idea, that we would represent a twist between any 2 frames, a relative twist between any frames, as, again, some speed. It's no longer just angular, it's just some speed. It's also 1 number. And we have here a screw. And we said that this screw is also a twist. So this is 6 numbers and this is 6 numbers. When we take the exponential map also of the tilde map of this screw, we would get now, we can relate the homogeneous transformation at any angle correspond with respect to the initial configuration or the initial pose that we have between these two frames. And this exponential map also goes from the Lie algebra of SC3 to the Lie group. We didn't discuss what the expression of this was. I'm going to show it to you in a bit. But why did we introduce the screw representation of twists? Because we want to model joints. And then in this language, joints would be modeled in the following way. A twist of the joint, okay, so we said that a joint is simply the relative twist. Okay, so the joint is put between two rigid bodies, so it restricts the relative twist of these two bodies. So body I and body I minus 1. So assuming we have this serial linkage, we have between body I minus 1 and body I, we have a joint. That the twist of this joint is equivalent to the twist of the relative twist of these two rigid bodies. And we have it simply given by the screw axis multiplied by some value, some speed, and this will be simply the joint angular velocity. Okay, if we have a prismatic joint, then this number would change its meaning. It will be the linear velocity along the screw axis. And when we have a prismatic joint, this screw axis takes this form. The first three numbers on the top are zeros, and the second three numbers are a unit vector. And this unit vector, intuitively or physically, it's represented by the axis along which this joint, okay, extends or retracts. Okay? So it has a very physical meaning, and you can do it just by inspection. So n hat is simply the axis along which this joint, okay, this prismatic joint extends or retracts. When we have revolute joint, the screw axis completely changes its meaning, or at least its form. And what we're going to have when we have a revolute joint is that we're going to have three numbers on the top and three numbers on the bottom. So it's 6 numbers in the end. The 3 numbers on the top are the axis around which this revolute joint is rotating. So again, it's now the revolution axis. While the second 3 numbers is a cross product between two things. The first 3 numbers that we had, which is the axis, and any point on this axis. So you see here, so Q there is any point along the axis. And simply when you calculate this, you choose the easiest Q, right? And the easiest Q is simply the one that will make the calculation easier. But you can prove, and this will be part of the assignment, inshallah, that any point changing the Q and taking this cross product will not change the result. Okay? So that's why it's a unique way of defining this. Then by having this screw representation of twists, we showed that the end effector pose with respect to the stationary frame is given by this extremely fancy, I would say, formula, and this is known as the product of exponentials formula. It was attributed to Brockett. Again, this is the first person or first scientist who actually introduced it in robotics. And it simply says that if I know the initial pose at time 0, so and what I mean by at time 0, I mean here at home position, the value of so the relative pose of the end effector with respect to the stationary frame, when all of the angles theta, so theta here is a vector of all of the joint angles, when all of the angles theta are 0. So the home position, what you choose as the home position for the robot, and then you would simply multiply this in this order by all of the twists, all of these relative twists between link n and link n minus 1, and up till link 2 and link 1 and link 1 and link 0. And you see all of these are, so this is the screw axis of joint 0, joint 1, screw axis of joint 2, up till screw axis of joint n. And we have this matrix exponential, again, which is a map that will take the 6 numbers and give us a homogeneous transformation in the end. So this is just a homogeneous transformation that's constant, multiplied by homogeneous transformation that's a function of theta n, homogeneous transformation is a function of theta 2 up till theta 1. Just a side note that's very important, and it's also we're going to be needing it, but you can deduce it easily from this formula, is that if you're interested not only in the end effector pose, but in any pose in between, okay, of any point there, simply add a frame there and calculate it by just cutting out this expression. So for example, if I'm interested here in the pose of the second frame, so frame number 2 with respect to the 0 frame, then I would simply multiply, then this would be h20 as a function of theta 1 and theta 2 only. And then I'm going to have here the exponential of S100 and here exponential of S210, and that's it. So I'm not going to be continuing. So I'm going to have a function of theta 1 and theta 2. Yeah, that's correct. Theta 1 and theta 2. And then in the end, I'm going to multiply. All of this will disappear. I'm going to multiply here by H20. Okay? And you can do that for any frame, okay? For any link or any even new frame that you add. So I can add here, for example, a frame in the middle at the center of mass. We're going to be needing this later for the dynamics. But if I add here a new frame at the center of mass, then I can calculate, again, the pose of this frame in the same way. Any questions so far? Yeah. Yeah. You mean of 3 with respect to 2. So you want the relative pose of link 3 with respect to link 2 is simply given by this expression. Multiply, if you want h2 with respect to h1 as a function only of of theta 2, then it will be the relative twist, but this is the catch, the relative twist between frame 2 and frame 1 expressed in frame 1. That's the difference. Okay, so what I'm using here in this expression is the 2, 1, 1, 3, 2, 2, n minus 1, n minus 1. But what we're using later on in this expression is 1, 0, 0, 2, 1, 0, n minus 1, 0. So we're expressing these twists or these screw axes in the inertial frame so that we can use it in this expression. I'm gonna get back to this in the end, okay? So that it's also very easy to transform this one to that one. Okay, we're gonna be getting to that later, inshallah. Yeah.
Because we want to use the Rodriguez formula, that's why we're not combining the exponentials. Because a lot of indices you can add the powers.
No, you cannot do that. And you asked this last time. You cannot do this. You cannot add, because this is not a nice scalar exponential. This is not that. This is just homogeneous transformation multiplied by homogeneous transformation multiplied by homogeneous transformation. You cannot add here the exponentials. No, I don't need. I need to get back to this, but I would say 90%, I'm sure it won't work. Okay. There's a 10% I might be wrong. Okay. But something to look into. Okay. But we don't need it. Okay. We don't need to actually combine all of this. We can simply do it in this way. And it's just a recursive formula. Okay. In terms of implementation. So this is the expression from the book of the matrix exponential. I was too lazy to write it again because it's the same idea. The first part. So again, remember that what is this calculating? We get in the end the homogeneous transformation. So I give you 6 numbers. So S here is 6 numbers. The first 3 and the second 3, they are called only in this slide omega and V. Okay. So only in this slide, they are called omega and V, and they have nothing to do with angular velocity and linear velocity. It's just that the first 3 here would correspond to this point, for example, if it's a prismatic, and this one if it's revolute. And the second 3, which is called in this slide V, would correspond to this term and to that term. Okay, so it's just a naming. So again, if S is given by this pair of 3 vectors, then we can calculate it in this case if we have a revolute joint, and in this case if we have a prismatic joint. And the prismatic joint is easier, so we get a homogeneous transformation where the rotation part is constant, is identity, which means we're not rotating. It also makes sense. And we have here some linear distance, and also this makes sense because it's just V is here is the axis along which you're moving, and theta is like how many meters. Okay, so in the end, you get meters in some direction. So this is the meaning of this expression. This expression is the same. So we have here a rotation matrix. How do we calculate this part? By the Rodriguez formula, because the Rodriguez formula would take an angular velocity, and you can calculate with it a rotation matrix, while this term in the end will just give us some 3 numbers that would correspond to some translation of the 2 frames of the 2 bodies with respect to each other. Okay, this is something you can just plug in the computer and it will do it for you. This is inshallah what we're going to be doing, what you're going to be doing in the assignment. Yep. Which one? This one? Yeah. What do you mean? Yeah.
So yeah, so it's a different calculation, right?
This part? You mean when there's a joint, when there is a revolute joint? Because when you have a revolute joint and you take some angle theta, you expect there will be some relative orientation, right? That's it. What is this R matrix? This new R of the body after you rotated it will be given by the Rodriguez formula. That's what this means. Yes, yeah.
The parabatic joint, theta is not, we're mentioning how many meters. Theta is not the angle as the hub.
Let's go back. If you go back to this slide, you see that theta dot is linear velocity. So theta is linear distance. That's why these numbers, they change. The meaning changes. Okay, the axis changes. It looks different. Okay, and even the theta dot completely means something else. You always remember this. If this corresponds to a prismatic joint, then you're talking about linear velocity and linear distance. While if you have a revolute joint, theta dot would correspond to an angular speed or an angular velocity, and the theta would correspond to an angle. This is what the notation of the book uses, and some other books would represent the joints by Q. So they would represent the joints by Q, so that Q makes sense if it's linear or if it's like rotating. But theta, I know it's like theta is always something that's rotating as notation wise. But this is the notation we're going to be sticking with. Okay, and it will be clear from the context whether it's a prismatic or a revolute joint. Now let's again practice this. See how easy is it to do this. So. As I've been told before that when I'm writing on the whiteboard, it doesn't appear in the video. So stick to your notes now, okay? There's nothing I can do about it. So let's see. Annotate. No. I want to go back. Okay, this is video. Okay.
Can you save the annotation? Like when you're going, you can, I think, save the annotation temporarily.
Okay. 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 Let's do it. Okay. Now let's see. Where is the stationary frame? It's placed up here. Why not there? It's going to make our life easier. Think about this zero frame being there, okay? And then we just added a new zero frame, let's call it zero dash, and we put it there. And as you know that having a constant transformation from any two frames is very easy, just a constant homogeneous transformation. But when we put the zero frame here, it will make our life very easy. And you'll see now why. Okay. So the first thing is, let's see. So we need to identify a number of things. We need to know okay, maybe let's go back. Let's write what we're trying to calculate here. We're trying to calculate the homogeneous transformation of the end effector frame, which is frame number 3, expressed in the spatial frame 0, as a function of how many joints do we have? 3. So we have theta 1, theta 2, and theta 3. And how is this calculated? Again, from the product of exponentials formula, we have the exponential of S1 with respect to 0 expressed in 0 in tilde form multiplied by theta 1. Then we have the exponential of S2 with respect to 1 expressed also in 0 in tilde form multiplied by theta 2. And we have the exponential of S3 with respect to 2 expressed in the 0 frame multiplied by theta 3. Then we multiply in the end by the H3 0 when all values of 0. So we have 0 theta 1, 0 theta 2, and 0 theta 3, which is what we mean by the home configuration. And this is the home configuration. Okay. So when we put all of the joint angles to 0, this is where the robot will be. So this is a revolute joint that it does an axis like this, rotation like this. This is a revolute joint that rotates like that. And this revolute joint rotates like this. Okay. Yeah.
is that we don't have the frames, for example, in this case, we have the frames saved by the same example. But
Yeah.
because that we don't, is there any standard way to set each frame?
For our calculations, what we're doing here, put the frames at the joints. That's it. Orientation is completely your call. It makes sense because of the calculations we're going to be doing is to align at least one, not at least, only one of the coordinate frames, one of the axes of the coordinate frame in the joint axis. You can, of course, in general, you can choose, for example, frame number 2 to be a funny orientation. And this, again, will be an axis, okay, that's has components in X and Y and Z, but it does, again, you're just making your life hard. So we always put the frames aligned with the joint axis. Okay. Which one is, should I choose this one to be X or Y or Z? It's your call. It doesn't change anything. So what the first thing let's calculate is H3 with respect to 0 in the home configuration. And the H is nothing else than two components, right? The R3 with respect to 0 and the psi of 3 with respect to 0. Let's start with the second one, with the psi. So how can I reach from this frame this point? Because the psi 3, 0, what does it mean? It means the origin of frame number 3 as seen from or expressed in the 0 frame. So give me some numbers. The first number I should put here is how much should I move in this direction? So L1 and 0 minus L2. Everyone agrees? Everyone agrees? So
Join to the second and third.
no.
To the 0.
The origin of the third frame expressed in the 0 frame. That's it.
Y minus L2 according to the axis of the 0 frame.
Expressed in which frame? So if you're at the 0 frame, how should you move to reach this point? This is how it is. I move in this direction. Again, so these two frames are at the same point. They are coincident. They're just drawn like this for simplicity. So theta 0 and frame 0 is the same as frame 1 here. So I move in this direction by L1 and in this direction, which is the Y1 by 0. I don't move in this direction. And I move in this direction by negative L2. So L1 in the X, L2 in the minus L2 in the Z would make me reach from the origin of this frame to the origin of that frame.
So from 1 to 3 in terms of the minus.
From 0 to 3. Yeah, that's right. Which is the same as 3 as seen from 1. So 3 as seen from 1. No, if you're think of it this way, if you're at frame 0, where do you see frame 3? Where do you see the origin of frame 3? Let's put it this way. Have a question? Which one? This one, L1 0 minus L2. So let's maybe do something in between. Let's do R1 0 and psi 1 0. If you are at frame 0 and you want to go to frame 1, again, both are at the same point that they have the same orientation with respect to each other. So what do you think psi 1 0 would be? Would be 0 0 0. I don't need to go anywhere to reach frame 1 from frame 0. Okay? What orientation, what is the relative orientation between frame 1 and frame 0? There is no relative orientation. What does that mean? It's the identity element. Let's do R2 0 and psi 2 0. What about R2? Okay, the R2 0 to be a little tricky. What about psi 2 0? How do I reach this frame from that frame? Again, we're talking only about the origin. So how do I reach this point starting from here? I should just move in this direction by how much distance? L1. So it's L1 in the X1, the head direction, and 0 0 in the rest. So it's L1 and 0 and 0. So if I can reach this frame by moving in this direction by L1, what else should I do to reach that frame? I should go down by L2, which is down here means it's minus Z. Clear? Clear? What about R2? And what about the orientations? R2, 0, and R3, 0. There's something we didn't talk about. Again, if you took any course before on rotation matrices, this should be easy to you. If not, think of it this way. The relative orientation between any two frames, the components inside are simply, let's write it here. So if I want to have Ri with respect to J, and this is a 3 by 3 matrix, so I have one column here, one column here, and one column here. The first column of this Rij matrix is how do you see, or how is the ith axis, so how is the x-axis of the I frame seen from the J frame? And the second one is how is the y-axis of the I frame seen from the J frame? And the third one is how is the z-axis of the I frame seen from the J frame? Okay. And seen, how do you represent axes now? You simply do the projection, which is the dot product. Okay. Now let's put this in practice. So x2, okay, x2 hat. How do you see it from this frame? It is the same as which frame? It's the same as which axis? As the minus z1 hat, right? So x2 hat is the same as minus z1 hat. Z1 hat is up, x2 hat is down, so they are minus of each other. So if I want to represent this as a 3 by 3 matrix, the first column here, which would be the x2 hat seen in the 0 frame, would be 0, 0, minus 1. What about the y2 hat? The y2 hat is the same as which axis? As the x0 hat, which means that it's 1, 0, 0. What about the z2 hat? Is the minus of y1 hat. 0, minus 1, 0. So this is the rotation matrix.
The theta into like theta component into the rotation.
You mean because we're going to be rotating, right? Very good point. Excellent point. Theta will start moving around, right? Do we care? This is the power of the product of exponentials formula. We do everything in the home configuration. That's it. And you plug it into the product of exponential formula, it will calculate everything for you. This later today. Later. We're going to be doing. Wait, you're very eager to jump. Okay, well, we're coming there. So R30 again quickly. We have x3 hat is in which direction? Y3 hat, Z3 hat. Okay. You can never make mistakes in these. Why? You can never get the rotation matrices wrong. Why? You have always a check that you can do. What is it? No. What is the check you can always check to see whether the rotation matrix is correct or not? The determinant should be equal 1. Determinant should be equal to 1. Right? Okay. So this is these are the constant parts. What about here the screw axis? So S1, 0, 0. I have 3. First of all, is it revolute or prismatic? It's revolute. This means it will have some omega and some v. Remember, the omega and the v are just what the book called. Okay. So this is omega 1. We're just going to be calling omega 1 and v1. Okay. These are 3 numbers and these are 3 numbers. The first 3 numbers, they should be a direction. They should be a unit vector. And it should be the direction around which this joint is rotating. What is the direction around which joint 1, theta 1 is rotating? Expressed in which frame? Very important. Expressed in the 0 frame. Okay. So around which frame are we rotating? Is theta 1? It's the Z, right? So this is the 0, 0, 1. The second 3 numbers, there's an easier way we're going to be doing it. Remember, it was the cross product of what? of this guy and some point on this axis. When you calculate it on paper, you don't need to calculate these numbers because the computer can do the cross product for you. You can never make it wrong. Okay. So what you can easily do instead of calculating the S directly, let's just calculate here or write down the omega and the Q. Okay. So the omega you said is 0, 0, 1. What about the Q? Choose any point you wish that sticks, that it lives on the line, so it lies on the line. So this is the axis we're talking about. This is S1, 0, 0. So this is, sorry. This is only S1, 0. I'm not expressing it in any frames, right? This is just the abstract line. Here, this is the abstract line, S2, 1. And this is the abstract line, S3, 2. Yep. So choose any point on the line, 0, 0, 0, right? Everyone agrees? So 0, 0, 0. The cross product of the 0 with anything would be 0. What about the second axis? So S2, 1 in the 0. I need to represent its direction, omega 1 and Q1. So around which axis am I rotating? Positive or negative? You have to here choose, again, this is where you choose the convention of the theta. So the theta is defined like this. So in which axis is this? Remember, if you look here, it's in the Z2 axis. But we're calculating which, so in other words, if you say I want to have S2, if you're calculating S2, 1, 1, no, S2, 1, 2. S2, 1, 2, and the first three numbers will be the Z2 hat, right? It will be 0, 0, 1. But we're not interested in representing it in the 2 frame. We're representing in the 0 frame. So I have to look at this axis as seen from this frame, which is the same as the 0 frame. So what is this number? Minus y hat. So 0, minus 1, 0. Okay. What about the Q1? Choose any point on that line. 0, 0. The point, okay, the point that we chose in the first case, let's put it here by red. The point we chose in this first case is this point. The point we chose in the second case is that point. And again, it's a choice. Okay? Because if you choose a point here, it will give the same number. But we choose this one because it makes our life easier. And then last but not least is S3, 2 in the 0 frame. I also have omega 2 and Q2. What is omega 2? Again. Okay, sorry. I just apologize here for the naming. This is bad naming. Maybe let's call these. Let's call this omega 1, Q1, omega 2, Q2, omega 3, Q3. This makes more sense. Okay. So the omega 3 is of the 3 frame. So corresponding to theta 3. So theta 3 is rotating like this, which is in which frame? X1 hat, which is 1, 0, 0. What about the Q3 point? Which point do you choose? We choose the origin. So we're going to have L1, 0, minus L2. Can someone beat that number? Is there any better point to choose? Very good. No, not very good. No. Yeah, there's a minus. Yeah. What? 0, 0, minus L2. 0, 0, minus L2 is a better point. Why? Let's check here. So we can extend this frame like this. And you see that this point here on this axis, okay, seen from this frame is easier to represent than this point. Okay, both of them lie on the axis, but this is one much easier, right?
Assuming no distance is here.
You mean left and right? And then there is no distance. Yeah, exactly. So this frame is exactly aligned with this point. Yeah, that's right. Yeah.
Apart when we get them, will it be affected like clockwise and counterclockwise writing the
Yeah, it affects because here the theta 3, this is the positive axis about it. So we have to take this into account. If I was rotating theta 3 like that, then this direction would have changed, would have been -1, not +1. So here, for example, you see this is 1, 0, 0. This is 0, -1, 0, and this is 0, 0, 1. So the direction makes into the convention you choose for the theta plays a role here in the axis. So the axis has to be according to the right-hand rule. Easy? Okay.
So, Professor, for the square axis,
Yeah.
if it is a revolute joint, we don't care about the last three numbers being unit vectors.
Very good point. Very good point. When we talked about revolute and prismatic, the prismatic joint had the first three numbers as 0. The second three numbers was a unit vector. So in the end, S is a unit vector or not? Yes. So when you have a prismatic joint, S in the end has a unit magnitude. If you have a revolute joint and you calculate here, the first three numbers will be a unit vector, but the second three numbers will not be a unit vector. And we don't care because S is not unit in any sense. It's called, I don't even think I mentioned it in this name, but last lecture, but you can check. If I called it a unit twist, has nothing to do with being a unit vector. Okay? So it's a twist with constant magnitude. That's not one. Okay? And it's a constant in space also. The cross product, exactly. So you're going to be crossing that you're going to be doing a cross product with a unit vector with some number, okay, with some vector here, which definitely will not be a unit vector. Okay? And even if it was a unit vector, if you have two unit vectors, this doesn't make the 6 numbers a unit vector, right? Because you need to divide by the magnitude of the 6 numbers together to make it a unit vector. So it's in no sense it's a unit 6 numbers. Right? Okay, let's see how we save this. Save. Okay. We have another example, but again, you see, it's easy. And the other example is in the solution is in the book, and you're going to have plenty of examples to play around in the homework and the assignment. So, okay, so I think you're safe now to move on. Yeah. For which one? Yeah. You mean to represent it in a? Yeah. We represent them in the 0 frame. Yeah, we represent all of it. Everything is represented in the 0 frame. So if we go back here, you'll find that. See. So they are represented in the star frame. So this should be represented in the star frame, and this should be represented in the star frame, so that it can be calculated. And when we use it here, we represent them in the 0 frame. Okay. Now let's do something. Okay. Let's move on. So we have a map between the joint angles and an element of SE3, right? Which is the pose of the end effector. And we said that we can do the same for joint angles to any point or any pose of any link that you're interested in on the whole robot. So we have a map that goes from the joint space, so where the joints live, we're going to be calling it Q. It has the name of joint space. It's a manifold that has n dimensions. We're not going to talk about how it looks like and the topology of it. Okay, this will take some time from us. But if you're interested, you can look at it at your own pace. What we're interested in is the differential of this map. So I have a map that goes from Q to SE3. The differential of that map will go from the tangent space at theta, the tangent space of Q at theta, to the tangent space of SE3 at H. In other words, we want a map that goes from theta dot to h dot. Okay? So we want a map that goes from the velocities. So we have a map that goes from the angles to the pose. We want a map that goes from the angular rate, right, the angular velocities, to the h dot. And since we have something with respect to the h dot, what can we do with it? What we can represent it in what? In the algebra. Can transform the h dot to the algebra. And when we have 6 numbers in the algebra, again, the skew symmetric form in the algebra, what can we do with it? We can represent it as 6 numbers. So we can represent a map that goes from 6 numbers, okay, which is the theta dots, theta 1 dot, theta 2 dot, theta 3 dot, up till theta n dot, to the twist, to the end effector twist, again, expressed in any frame. And this map that goes from theta dot to v, to the twist, is known as the Jacobian. It's known as the geometric Jacobian, because we want to differentiate between the Jacobian in general. There's something called the Jacobian in general. Okay, you might have calculated yourself, or more properly, it's known as the analytical Jacobian. But we're talking here about the geometric Jacobian. This geometric Jacobian, you can think of it this way. And of course, it's a 6 by n matrix. So the Jacobian is a 6 by n matrix because it will multiply the n angular rates here and give you in the end 6 twist components. And I can represent it either in the n frame or in the 0 frame. If I represent it in the 0 frame, we call this Jacobian the spatial Jacobian. If I represent it in the n frame, I call it the body Jacobian, or the end effector Jacobian. Easy?
It's different from
What omega here?
but this components.
There's no omega here. Again, the omega, you mean the 3 numbers here? But we're talking here about the angular rates, right? Angular rates of the joints, okay? Which is a velocity. But again, you have a lot of things that are moving now. Okay? So the twist has 3 numbers, 6 numbers. The first 3 on the top is an angular velocity of frame n with respect to frame 0 expressed in frame 0. But this is something else. They both have the units of rad per second. That's correct. But they're something different. This spatial Jacobian is very important, extremely important, more than you can think. Okay? So we're going to spend some time in deriving it. What do we need to derive it? Nothing else than what we already know. So we're going to just do some nice math. Okay, not so nice. But again, you're going to watch. We're not going to be writing it. I'm just going to like shock you with the slides. So some properties you should know. Hn with respect to 0 is h1 with respect to 0 multiplied by h2 with respect to 1 and blah, 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 up to n minus, n with respect to n minus 1. Everyone knows it? The inverse of the product of 2 matrices is the first one in the second one inverse multiplied by the first one inverse. Clear? The inverse of the relative pose of I with respect to k is nothing else than the pose of k with respect to I. Makes sense. Yeah. That's a good point. Is the transpose of the homogeneous transformation equal to this expression? We don't have that. You don't have that the transpose of a homogeneous transformation is a homogeneous transformation. We don't have that anymore. It's only for rotation matrices. How do we define the tilde form of the twist of the n frame with respect to the 0 frame expressed in the 0 frame, which is the spatial twist? Okay? So this is the twist of the end effector with respect to the fixed world expressed in the fixed world. How do we calculate it? Again, h dot multiplied by h inverse, right? So h dot is simply the time derivative of this expression from here. And the h inverse is simply the inverse of all of these homogeneous transformations multiplied by each other. Okay. The first one, we took it as it is. The second one, we inverted all of the indices and we inverted the order. Okay. So we inverted all of the indices and we inverted the order. So this becomes, the first one becomes n. So instead of the last one being n minus 1, the first one here will be n minus 1 n, and so on and so forth until you reach 0 to 1. Easy. When you have the rate of change of a number of matrices multiplied by each other, what do you get? Or another, for simplicity, the rate of change of A multiplied by B will be what? A dot, the product rule, A dot multiplied by B plus A multiplied by B dot. It doesn't commute. You have to keep the order the same. So if it's A multiplied by B, then the rate of change of it will be A dot multiplied by B plus A multiplied by B dot. Clear? Let's do the same here. So I'm going to take the we have here again, remember we have a lot of in between. So these dots means that you just have, you go from n, you go from 1, 2, 3, 4, 5, 6, 7, 8 until n minus 1. Okay. We have this expression. Take a look at it for a second. Get yourself comfortable with it. So this expression, we differentiated the first one, so we got h10 dot multiplied by the rest are the same. And then up till here, we took this part and we multiplied there, right? No, not yet. Okay. Then we have the second part. We kept the first one fixed, and then we differentiated the second one. So we have this one here. And then we took everything after it, and everything there, we just added up until you reach this part. Okay. These expressions, what will happen to them? Identity. All of these expressions will disappear. Why is that? Take a look at this one, at least. So hn minus 1 multiplied by hn minus 1n is the identity. We have the same here. So we're going to have these two to be the identity. The ones before will be n minus 2, n minus 1, and the one here will be n minus 1, n minus 2. Identity. Up until you reach 2 and 3 and 3 and 2. Cancel out. So everything here will cancel out. And you're going to get, in the end, this part, and this part in the second term, and this part in the last term. Take, again, a moment to get comfortable with. Let's go back. Nope. So this expression, so in the first term, this one and this one will remain. In the second term, this one and this one, and this one and this one remain. Everything in between will disappear, and so on. Also this term, so this is h01, and this is h12, up until you reach n minus 2 and minus 1. So all of this you can combine together to get something like this, h0 and minus 1. What does this remind you of? Twist in tilde form. So what is this twist in tilde form? It will be 1 with respect to 0 expressed in 0. 1 with respect to 0 expressed in 0. This one in between will be 2 with respect to 1 expressed in 1, up until n minus 1 expressed in n minus 1. What does this expression remind you of? The map that would transform the tilde form of the twist. So if I have this to be 2 with respect to 1 expressed in 1, and then I multiply it from the right and the left by 0, 1, and 1, 0. What do I get in the end? What am I transforming this twist into? To be 2, 1 expressed in, the same as this one, expressed in frame 0. So in the end, we're going to have something like this. Let's look at this, what this means. Let's see whether it's something intuitive or not. The twist of the end effector, or frame n, with respect to the stationary frame, expressed in the stationary frame, is equal to the twist of 1 with respect to 0 expressed in 0, 2 with respect to 1 expressed in 0, 3 with respect to 2 expressed in 0, 4 with respect to 3 expressed in 0, up till n with respect to n minus 1 expressed in 0. If this is all in the tilde form, I can also have them very easily in the vector form, right? In the 6 vector form. And it makes complete sense. This is what you were introduced to velocities or positions a long time ago when we were talking about the planar case. So my velocity with respect to you is the same as my velocity with respect to you is the same as your velocity. Is the same as my velocity with respect to you, and your velocity plus your velocity with respect to him, and your velocity with respect to him, and your velocity with respect to him. Makes sense, right? It's very intuitive. If you ever worked with 2D dynamics, right, or 2D mechanics, or theta dot, like x dot and y dot and z dot, you know that this doesn't work. It works for twists, which is very powerful. Again, it's very intuitive. This is how we should have been taught velocities, right, and positions, right? Because my position with respect to you is your position, and so on. I can link them very easily like that. And this is the case. Now let's move a step further. We know that the ideal joint, so the relative twist between any two bodies, again, now we're assuming that all of these bodies are connected by joints. So the relative twist between the ith frame or the ith body and the I minus 1th body expressed in any frame is some sort of screw axis multiplied by some theta dot. So I can write them in this form. Okay. So again, let's go back a little bit. You remember, so we had this expression, okay? So this one, which is Vn0 is equal to V1, 0, 0, 2, 1, 0, 0, 2, 1, 0, and n minus 1, 0 is the same as this one. But we're going to be interested in this one, which is nothing else than representing the relative twist of 2 with respect to 1 in 1, and then transforming it from 1 to 0. Representing the relative twist of n between n and n minus 1 in n minus 1, and then transforming it to 0. Why are we doing that? Can anyone guess? Why are we writing in this way?
Because the measurement resource or measure the local.
But why are we representing it in the n minus 1 frame? What happens when we do that? Or in other words, what happens when we represent the I minus 1 screw in the I or the I minus 1 frame? What happens to it? It becomes what? It becomes a constant. If you go back to the image that to the example that we did. If you look at, for example, I'm moving my hand like this. So I'm rotating around this axis, right? So as seen from this object around which I'm attached to it in this moment, I'm constant or not? I'm not changing. But if you represent it with respect to the 0 frame, and for example, I'm starting to move like this, you see what happens to the axis? It changes. So these guys, okay, so again, these guys are a function of theta. They're no longer constant. But this one is always constant. Again, so when I transform this constant twist to the 0 frame, it becomes a function of theta because I'm moving. Someone had this question, I think it was used yet. You ask about what happens when we start moving. If I'm looking at the vector, if I'm looking at this axis, the screw axis, in one of the two frames around which I'm rotating, it becomes a constant. But if I look at it from the 0 frame, it starts moving. So let's write it in this way because we know that this is a constant, and then we can have it expressed in this way. And again, so I can introduce this new notation, which is S n minus 1 expressed in the 0 frame, which is this term, 2, 1, 1, and then I transform it from 1 to 0, so it's 2, 1 in the 0 frame. But you see, this is a function of theta now, and this is a function of theta. The first one is 0, okay? The first one is constant, because we don't rotate around anything. And I'm just going to rewrite it in this form. And we have our map, the J. Okay? So each one of these columns of the Jacobian has a physical meaning. We're not talking about some numbers here. It has a physical meaning. What is the first column of the Jacobian matrix? Is the relative twist between link number 1 and link number 0, or in other words, it's the screw axis of joint number 1 expressed in the 0 frame. What about the second column? Is the screw axis of the second joint expressed in the 0 frame. The nth column is the screw axis of the nth joint expressed in the 0 frame. Has an extremely physical meaning. And then you multiply by theta 1 dot and theta 2 dot and theta 3 dot. Makes sense. So what is the dimension of this? What's the dimension of each one of these S's? It's a 6 by 1. So this is 6 by 1, and I put next to it a 6 by 1, up until I put n 6 by 1s next to each other, which makes it into a 6 by n matrix. Multiply by an n by 1 vector, will in the end map this theta dot, these n theta dots, to the twist of the end effector frame expressed in the 0, with respect to the 0 frame expressed in the 0 frame. Summary. This is everything you need to know about kinematics. It's only in one slide. That's it. the forward kinematics of an n-link open chain manipulator is given by the product of exponentials formula. The spatial Jacobian relates the joint rates, which are 6 numbers, to the spatial end effectors twist by this expression, again, by the expression that V is equal to J multiplied by theta dot. The J contains n column vectors. The kth column of the J matrix is given by this expression. Okay. And this part here is a constant. All of these are also constants. Now, if you look at this from an implementation point of view, from an algorithmic point of view, what is it that we're doing? This is extremely systematic approach. Okay? By systematic, I mean it's no-brainer. Okay, so if you have a very complicated robot, okay, you don't need to do any calculations in terms of your mind. You just need to, example as we did, you need to just to define what are the screw axes, okay, seen from the 0 frame. But even better, the only thing I need to provide is the screw axis expressed in the k-1 frame only. That's it. And also I need to give extra information, which is the transformation between each one of these, the intermediate joint lengths, the joint frames in the 0 configuration, in the home configuration. This is the only information I need to provide, which is completely constant. You draw the robot in the home configuration, you identify all of these quantities. Again, this will be K homogeneous transformations and N homogeneous transformations for the N links. And this will be N screw axes for the N joints that we have. Okay. And this is, this is the same also. These are N homogeneous transformations for also the joints. All of these frames are put at the joints. Okay, so this is for simplicity. We put all of the joints, all of these frames at the joints. You align them with the rotation axis or the translation axis if it's a prismatic joint. You have inside of here a program that implements these two expressions. And in the end, the output is the HK with respect to 0 of all of the links. For each link, because we attached a body fixed frame. So if I want to know what is the pose of the first link and the second link and the third link up till the end effector, I'm going to have here n new poses as a function of theta now. And I'm going to have this, I'm going to be using these expressions here. If you go back, you see we're going to be using each of these individual expressions when transforming this constant screw axes into the ones that are make the columns of the J, of the Jacobian. So in the end, we get the Jacobian. And if we want to get the body Jacobian, which is also very important, plays another important role. Each one of these column vectors was a twist expressed in the 0 frame. How do you transform twists from the 0 frame to the end effector frame? By multiplying by the adjoint from 0 to n. Where do I get the adjoint from the 0 to n? Is the inverse of the n with respect to 0. Where do I get the n with respect to 0? I got it from here, from one of these calculations. The last thing is this part, right? Do I need to provide the SK with respect to k-1 expressed in the 0 frame and also expressed in the k-1 frame? So the example we did, we represented the screw axis always in the 0 frame, not in the k-1 frame. Do I need to do it twice? Do I need to represent every screw axis in the k-1 frame and also in the 0 frame? No. You only need to provide it in the k-1 frame. And we have this expression that will transform it to the 0 frame. What is this expression? It simply says that I use the transformation from the k-1 frame to the 0 frame in the home configuration. This is a constant vector. This is a constant matrix, and this is a constant vector. I'm going to have this. I can even do it in a pre-processing way. It's not needed in the algorithm itself. And that's it. Easy?
Question, Prof.
Yeah.
For prismatic joint, will the frame from the end effector to the joint for prismatic joint, will it be a constant?
Again?
For a prismatic joint.
Yeah.
The frame at the end effector. as well as the frame before the just before the prismatic joint, will it be a constant? The link length.
Let's see. So
Let's assume at this end we have a prismatic joint.
yeah,
Between B and there's a
there it is. This is a prismatic joint. Okay.
If it's moving there, do we have a fixed length between the frames, the consecutive frames between the prismatic joints?
When the joints extend, no. So L1 will change when it starts to extend. But we don't care, right? Because we do everything in the home configuration. You get the transformation from this frame with respect to that frame only in the home configuration.
Okay, so the calculations take care of whatever happens.
Exactly. That's why you draw only one figure like that, okay, in the home configuration. You identify where are all of the axes, and you try to work it out.
Does that imply that if I'm using the robot over and over again, I have to calibrate the home configuration?
The home config, okay, that's a good point. So the home configuration has to be, you have to go back to it in some sense. If you're using, again, this is an implementation issue. If you're using, for example, some sensors in between that don't have this home position, for example, you can use joints and you can have sensors on them or encoders. Okay, I don't know if you have implementation details, but if you're using incremental encoders, for example, you don't have a home position in an incremental encoder. So you need to define in some way in the robot itself, where is the home position? Usually one easy fix is to put limit switches, for example, so that when the robot goes back to this like joint locations, this is the 0 position. And then you can always start from there. Okay, this is one way of doing it. Again, a basic way. Of course, different companies would do it different ways. Any questions? So this is everything in the kinematics. Yeah.
It's the same for other system of robotics.
Or for other what?
This is for robotic arm.
For robotic arm. For open chain linkages.
Robotics the same.
You mean other robotics as in?
Kinematics, for example, for quadcopter.
Okay, for the quadrotor, we already done that. Okay. So the quadrotor was you had also unit like axes that where the propellers apply the thrust. And you had something like the Jacobian. Okay, something like it. It's not the same. You had something like the Jacobian. Let's go back. You had something like the Jacobian that relates the wrench, right? That's applied on the robot to the individual thrusts or the individual forces that you had from each propeller. So you had something the same. And if you had the tilt rotor, also the mapping in between was also a function of the angle in between. Okay. I didn't want to talk about it today, but again, since you asked, this map is a map from velocities to velocities, right? What would be the map from the dual variable of angular velocities and the dual variable of the twist? First of all, what's the dual variable of the twist? The wrench at the end effector. What about the dual variable to all of these angular velocities of the joints? The torques, the motor torques that you apply. What would be this map? No, there's no dynamic equation. You don't need from either from wrench to torque. Say from wrench to torque, what would it be? What? No, much easier than that. The transpose. Who said the transpose? Don't be shy. Okay. So the transpose, yeah. So again, let's see. Let's annotate. Nope. So we have that. I go from the theta dot to the Vn0n by the Jacobian, okay, as a function of theta. Then the dual of this twist of something that's applied on the body expressed in the n frame. So this is applied on the body expressed in the n frame. Some wrench, for example, from propellers, from gravity, from anything. and then we have here the transpose of this matrix will map us to the torques. Exactly the same. So you see here why the Jacobian is very important, because if I, for example, okay, this is something I was planning to do, but again, we don't have any time. We didn't even have time for the examples, okay, so you can have a lot of homework to do. So imagine that you want to have, okay, you want to have a robot arm, and what happens when you put all of the torques to be zero? The gravity makes it fall down, right? So the first thing that people do, when the basic thing, when you want to have a robot arm that when you turn it on, it just stays there. What is it? Cancel the gravity. Gravity can compensation, right? What does gravity compensation mean? It means that I know what the wrench of the gravity at each link is. So I would compute the total gravity wrench, but I want to apply joint torques, right? So what is the torque that each motor should apply such that it counteracts the gravity and the robot would stay still? This expression. I would calculate what is the total wrench that should be applied, that's applied on the end effector, okay, from the gravity of all of the links. And then I map it by the Jacobian, and I get the torques, and I make the motor apply these torques. Something extremely similar to drones. When the basic thing of any drone is what? Is the hovering. If you want to have the hovering, again, we have in the hovering a map that goes from the lambdas to the wrench of the control on the, again, applied on the body, expressed in the body frame. And this map, we called it M. So if I want to have that the total wrench applied on the drone is equivalent to the gravity, such that I cancel the gravity. Cancel the gravity means what? Means hover. If you have something that cancel the gravity, it means it's hovering. So if I want to compute the wrench that makes the drone hover, and I have here M is also depending on theta. Again, remember, it depends also on the angles if you have something that's variable tilt. What should each propeller, what's the thrust that each propeller should apply? Again, I would use this map to go from this way. So I would use the M inverse or try to invert it in some way. What is the M and the Jn here? What was the relation between them? Just from the picture. The inverse, exactly. So the M matrix that we talked about before is nothing else than the inverse transpose of the Jacobian. Okay? So the inverse transpose, because the Jacobian transpose goes in this direction, and the thing that goes from the individual thrust or the individual torques to the wrench would be the inverse transpose. Okay? This is just an overview, okay? And this is everything you need to know about kinematics. Of course, it doesn't make any sense without practicing. That's why, inshallah, you're going to have a lot of fun during the next week, inshallah. Okay, so assignment 3 will be posted tomorrow, inshallah. If not tomorrow, then the day after. Then you're going to have a nice week, nice weekend also. You have also one extra day that's a break, so more effort. Next Sunday is off, so see you, inshallah, on Tuesday. Okay. Yeah. Sorry? As you wish. The longer the deadline, the more how the assignment will be. So you choose. I propose next Thursday. No, not this Thursday, the week after. Okay? Okay, so Thursday.